All right, we've done all the geometry we can stand. Now we're going to start in with some calculus. And to do that, we first have to define what a vector function is. So, the full term would be a vector valued function. So it's a function whose domain is scalars, but whose range is vectors. So we write it like this. Little r maps big R, the real numbers, into either R2 or R3. And again, in theory, this doesn't have to be 2 or 3. It could be any number. You could have, in a lot of computer systems, for instance, there might be 10,000 array sets, 10,000 variables in them. But in this class, we'll just stick with R2 and R3. And so we'll typically write these in component form. So we split this into our three pieces. F of t goes in the X slot or the I slot. G of t goes in the J slot, and H of t goes in the K slot. Make sure I'm recording. Yes, I am. These functions are all scalar functions, or component functions. So these are just regular one-variable functions like you'd see in Calc 1. And I like to think of them as gauges measuring a rocket's position. Latitude, longitude, and altitude. Those are three different coordinates. Now, again, this reason this works so well is that I, J, and K are orthogonal. And so because of that, we can work with each one independently. We can do our X's, our Y's, our Z's as three separate pieces. Let's talk about domain. Now, domain is the set of all values where if you put them in, you get a number out. So the domain is real numbers. So what real numbers can I put into this function so that it will not break? Well, the easiest way to do this is to get the three different components separately and then just take the intersection, the set of points that are in the domain of all three. So let's do that. For the x component, we had t cubed. Well, the domain of that is r. There's no number you can put into the cube function that will break it, so we can just say it's all real numbers. Second function was ln of 3 minus t. Now, if you think about logs, logs are defined wherever the input is positive. So we want 3 minus t to be strictly greater than 0. And that means 3 is greater than t, or t is less than 3. Unless the arrow is pointing at t in both cases, so these are the same thing. If you want to put that in interval form, it's negative infinity to 3. And for the third one, square root of t. Well, square root is defined when the argument is non-negative. So for square root, 0 is allowed. So in interval form, it would be bracket 0 to infinity. And this one, if you want to write in interval form, would be negative infinity to infinity. So we got three different intervals here. We want to write what is the intersection of them. What is in all three of these? Well, it has to be less than 3 and greater than or equal to 0. So the domain would be 0 to 3 with a bracket on the 0 and a parenthesis on the 3. So that's all there is to domain. If you can find the individual domains, you just find out the intersection of them, and that's the overall domain. Okay. So now we need to talk about limits. Now, calculus is all about limits. Didn't start that way, but since calculus was kind of messy when it first started, in the 1700s they came up with limits as a way of unifying it. And so if we can define what a limit is, then everything else in calculus should follow along with it. So here's what we're hoping will happen. If we're taking the limit of a vector function, we can do the limit of each individual piece separately. And so we really would like that to be the case, but we have to make sure that that makes sense. So let's think of this over. All right, now we'll talk a little about topology, which topology is the idea of what does it mean for things to be close together? What kind of shapes can we make? Well, limit as t goes to a of r of t is L. L is a vector here. We're saying if we let a time go to a, then r should get close to some L whenever the time gets close to a. What does that mean? All right, well, let's picture it. So I have a curve. R of t, if we think here's the origin, R of t is the curve traced out by the tip of the vector. So here might be R of t1, for instance. And let's, in red, let's call this vector L. This will be our limit. And so then we get closer, we get R of t2, R of t3, and so on. Now as t gets close to a, we're hoping that the r's get close to L. What does it mean for them to be close together? What does it mean for two vectors to be close together? And that sounds like an easy question, but it's honestly not. Well, our vectors can all be thought of as being based at the origin. So they all have the same starting point. It seems to me like they should be close if they have the same ending point. So we can say, let's draw a little circle around the end point. And let's say the circle is radius epsilon. Then we will say it is epsilon close if the tip of our vector is inside that circle. And this might be r of a plus delta. Maybe a little to the other side would be r of a minus delta. So we're saying as the t, the time, is close to a, delta some small time interval, is it true that the vectors will be inside this bubble? Well, let's think about what that means then. So we want to say that if epsilon greater than 0, and I left some space on the next slide to write in this and draw these pictures if you want. So the distance between r of t and vector L would be the distance of, let's see, r is f of t, g of t, h of t, and L1, L2, L3. If we break L into its pieces, they should just be 3 different numbers. That last should be a parenthesis, not a bracket. And this becomes square root of, remember our distance formula, f of t minus L1 squared plus g of t minus L2 squared plus h of t minus L3 squared. So those are my 3 different components. So what I am saying then is the only way this will be small, we want this to be really small, less than epsilon, it would mean that each of these individual pieces would also have to be small. And I'm not going to bother working out the exact values. It'd be like epsilon squared over 9 probably, because then you'd add... Now I'm not sure if that's... maybe it's 3. If this were a real analysis class, we would go in really detail and work out the exact values, but we'll just say small. All of these have to be small. Well, that will be true if f of t, the limit, t t goes to a is L1. If that limit is true, then this thing will get small when t gets close to a. And the same will be true for g of t and h of t. So we're saying for the big limit to work, for the whole thing to be less than epsilon, it must be each of the little limits work. Each of the little limits are L1, L2, L3. Well, that's exactly what we were hoping for. We have now said this is essentially a proof, albeit a kind of simplified one, which is saying the only way the big limit of the whole vector is vector L is if each of the little limits are the components of L. So that tells us that this is true. So you can go ahead and copy this down. The limit as t goes to L of bold R of t is the same as the limit of each one of the components individually. So, now that we know that, now that we are confident that we can just break limits up into pieces, we can charge full steam ahead at recreating all of calculus in a three-dimensional space. So, find the limit as t goes to 0 of r of t, where r of t is 1 plus t cubed I plus te to minus tj plus sine t over tk. Well, we just got to do the limits individually. Limit as t to 0 of r of t is bracket, or let's do ijk. Limit as t to 0, 1 plus t cubed I plus limit as t to 0 of te minus t j plus limit t to 0 sine t over t k. So we do these each individually. This is a polynomial, so we can just plug in 0 and we get 1 I. The rule with limits is always, if you can just plug it in and get a meaningful answer, go for it. Plug in 0 to this, we get 0 times e to the 0. E to 0 is 1. 0 times 1 is 0, so 0j. This third one, plugging in 0 doesn't work. It gets us 0 on top and 0 on bottom. So how do we do this limit? Well, this is one of the ones you learned back in Calc 1, and you're expected to remember that sine is about the same as just t when they're very small. The power series for sine of t was t minus the Taylor series. You remember doing these last semester. 3 factorial plus. And so when t is small, everything vanishes except for that first term, or the first term is the most important one, the t. You could also do this technically using L'Hopital's rule. That feels like a little bit of a cheat to me, and the reason being that you have to already know derivative of sine is cosine, and if you didn't know that, you would have to use this limit to get that, so it's kind of circular, but that's more theoretical than most people in this class would care about. That's the answer, 101. All right. Now, continuity. Continuity is a big concept in calculus. And the very informal method is to say it's continuous if you don't have to pick up your pencil. So when you draw the curve, it's connected and no breaks in it. But really what it means is that the limit as t approaches a is the same as if you just plugged in a. These both exist and they're equal to each other. So we've seen that limits can be split component-wise, so that means continuity can also be split component-wise. If the components are continuous, then the overall is continuous. So like this example here, since plugging in 0 doesn't work here, this function is not defined at 0, so it wouldn't be continuous there. But these functions are continuous everywhere else besides 0, so function bold r would be continuous everywhere except 0. Okay, so space curves. A space curve set of points where x, y, z equals f of t, g of t, h of t as t varies over some interval I. So we allow t to take values. We don't put any breaks in the t. and we end up sketching a curve in space that is what traced out by the vectors. So here's an example. Describe the curve defined by the vector function 1 plus t, 2 plus 5t, 1 minus 6t. Or negative 1 plus 6t, sorry. I'm going to show you an example, by the way, of the space curve. I just want to show you how I think of it. What I think of it as is one of these arms that draw. So imagine this is the origin here where this arm is based. The vector is the arrow that is this arm. It points from the origin out to the tip of the pencil. And then as the vector moves, the tip traces out a shape. And so that's kind of what's happening with space curves, that we are using a vector to trace out points, and then as it goes, it leaves a mark that is a curve. So that's how I think of vector space curves. So what is this? Describe the curve defined by the vector function. R is 1 plus t, y 2 plus 5t, and negative 1 plus 6t. Well, you might already realize that's going to be a line. It's specifically a line along the vector 1, 5, 6 through the point 1, 2, minus 1. So when t is 0, we would get 1, 2, negative 1. 1, 2, negative 1. When t equals 1, we'd get 2, 7, 5. 2, so that'd be out here somewhere, let's say, 2, 7, 5. And again, drawings do not have to be perfect. You get the general idea of it. And we can say t is in R because it says a line, so to be a full line, lines go to infinity, so we have to let the time go between negative infinity and positive infinity. All right. Let's do another one. Sketch the curve whose vector equation is R is cosine of ti plus sine of tj plus tk. This one comes out a lot. You'll be wise to remember this example because it shows up in a lot of problems. So the shape, let's look at the xy trace first. Just ignore z for a little. If we have x is cosine of t and y is sine of t, that describes the unit circle. And it's moving in the counterclockwise direction. That is standard, going back at least as far as Descartes, that counterclockwise is a positive direction. And we, I don't think I've said it yet, but make sure you put arrows on these space curves to indicate. Arrow indicates t increasing. So if you leave off the arrow, that is at least minus 1 point because it is supposed to represent something moving through space, so you need to indicate which direction it's moving. So if that's the case, then what is in 3 dimensions? We add in z equals t. Well, z is t, that means we would always be moving upward. So what we get is kind of a little slinky here, where we start this way. Notice as the first quadrant, x is increasing, y is, but z is also increasing. And so when we spiral back around, we should be higher up. I mean, a little dotted line to indicate that there's a negative part too from when time was negative. So that's what it would look like. If we want to graph this on our 3D graph, let's say add a space curve. X is cosine, Y is sine, and Z is t. And there it is, spiraling upward. We can even in this, we can push animate. This thing has a nice little feature. It shows how it changes over time. Don't worry about what those other arrows at the end are, but you can see this big blue arrow is the space curve showing where it is as time goes by. If you want to slow it down, or that didn't do that. No, that's not what I meant. Number of steps is what I meant to say. Or we could change it to be between time 1 or -1 and 1, and then it would show a shorter interval of time, but it would be the same thing. It's going around in a circle. If we look from above, you can see these are circles. And from above, it looks just like a single circle where it's rotating in the counterclockwise direction. We can see it's not... If we were looking straight down, we would just see a single circle. Since we're at a bit of an angle, we can see that it's getting broader as it goes upward. Or, well, it's not getting broader, but it looks like it from our perspective. Okay. Next. Find a vector equation for the line segment that joins point P, 1, 3, -2 to point Q, 2, -1, 3. Now it says line segment. So if before we said the time went from -infinity to infinity because we wanted it to be an entire line. Since we only want part of a line, it'll be the same equation, but we'll have to restrict the domain. So say PQ is P minus, or Q minus P would give us 1, -4, 5. And then a starting point, if we make P our starting point, then OP, which is the vector connecting the origin to our starting point, is 1, 3, -2. Because the vector is still based at the origin. So then R of T would be the vector, this is PQ is the velocity vector, would be 1, -4, 5, T plus 1, 3, -2. And time goes from 0 to 1. And it's pretty standard with these problems that if you want an interval, you set it so time goes 0 to 1. And you can check this. If you plug in 0, you'll get 1, 3, -2, which was your starting point, P. If you plug in 1, you would get 2, -1, -3, which was the ending point, Q. The other way to do that, the alternate method, there was a shortcut formula that was in our 12.5a lecture, which is R of T would equal T times, I guess, OQ plus 1 minus T times vector OP. So when we say vector OQ, it's just the point Q, but as a vector instead of a point. So this would make it R of T would be T 2, -1, 3 plus 1 minus T that should not be a that should just be a scalar. 1 minus T what's Q? 1, 3, -2. And again, you can check that. If I plug in 0 for T, I get 1, 3, -2. If I plug in 1 for T, this part zeroes out, and I get 2, -1, 3. If you were to expand this thing, 2T, -T, 3T, plus 1 minus T, 3 minus 3T, -2 plus 2T, and then add these together, you would get 1 plus T, 3 minus 4T, and -2 plus 5T, which is the same thing you'll get here if you expand it out, because you get, here's the T's, and here's the constants. But we really need to state that 0 is less than or equal to t is less than or equal to 1. If this were on a test and it said, give me the line segment connecting these, and you did not include the domain, that would be wrong. Because as a rule, in most math, if you don't state the domain, you just assume it's the biggest domain possible. And so if you didn't say it, I would assume you meant the whole line, not just the segment. So you do need to indicate what the domain is for line segments. All right. Find a vector function represents the curve of intersection of a cylinder x squared plus y squared plus 1 and the plane y plus z equals 2. Let's get an idea of what that looks like first. X squared plus y squared is 1. Get rid of that. So we want an implicit surface. X squared plus y squared equals 1. And the other implicit surface was y plus z is 2. Make sure I got that right. Yeah, y plus z is 2. And so if we look at that, we can see where it cuts through. Let's let z go a little lower so that we can see the whole thing. That's didn't help. Oh no, it's the positive. Oh no, it's positive z. We need z to go higher, not lower. There we go. And I guess, oh yeah, y needs the y, negative y is that direction. Okay. Play around with these things. You learn a lot just playing around with the sliders. That's still not working the way I want. I don't know. Nothing ever works the way you want. Have to do it for this one as well. 4 minus 4, 4 minus 4, 4. All right, there we go. And we can see if we cut there, it looks kind of like a circle, but maybe it's not. We need to figure out what the equation for that intersection is. So, we are told the cylinder is x squared plus y squared equals 1. Now, here's another thing you should probably commit to memory. X squared plus y squared equals r squared. We get x would be r cosine of t. Y is r sine of t. So again, it's the unit circle. X is cosine, y is sine. But if you scale it up, in this case we don't, but in other cases it might be a larger radius, so you just put that multiple in front. So we're going to use that to parameterize this circle. So this is the standard parameterization for a circle. X is cosine t, y is sine t, and for a circle, t goes from 0 to 2 pi. Now what about z? Well, we were given y plus z equals 2. So then z equals 2 minus y. But we've said y is sine of t. So z would be 2 minus sine of t. So when you're making a curve, you only want there to be one variable, t. That's called your parameter. So you need to try to get rid of all the others. Let's take a look at that in our graph. Let's add a space curve. X is cosine of t. Y is sine of t. And z is 2 minus sine of t. And we can see that, we can see a little red line got cut there. That's exactly what we were hoping for. If I animate this, I'll bet I can see, yeah, the vector is right there on that the whole time. There's two different vectors. The blue one is the vector pointing. Yeah, the blue vector is the one pointing to the curve. So we can see that the blue vector is tracing it out. The black and green vectors here are velocity and acceleration, but we're not talking about those yet, so don't worry about them. Okay, so that worked. Let's do another similar example. Find parametric equations for the curve of intersection of the paraboloid 4y equals x squared plus z squared and the plane y equals x. So 4y equals x squared plus z squared. Let's get rid of this one. This is this shape here. And the plane was y equals x. Yes. Y equals x. A little satellite dish here. Okay, and then we cut across. We get another kind of, maybe that's a circle, or maybe it's an ellipse. Well, let's find out. Okay, so we have 4x equals x squared plus z squared, and we have y equals x. So I'm going to try to reduce the variables a bit. I'm going to, wait, hold on. I wrote that down. Did I write that down right? It was 4y. I got ahead of myself. I'm going to get rid of that y and replace it with an x. So I will get 4x equals x squared plus z squared. You know, might as well make it a little easier. And now when I see this, when I see there's a couple squares and a loose linear term, I should be thinking, well, I want to complete the square. So I get 0 equals x squared minus 4x plus z squared. So half of 4 is 2, so square that, we get plus 4, and we get a plus 4 over here. So 4 equals x minus 2 squared plus z minus 0 squared. So this is a circle. Center is 2, 0. Radius is 2. Now, how do we parameterize this? Because we said earlier, x is cosine, y is sine, and now we don't have y, we have z. Well, x, y, z are just names. What we've got is a thing squared plus another thing squared equals 4, or 2 squared. So we can just call this whole piece here cosine, and this whole piece sine. So x minus 2 is cosine of t. So then x is cosine of t plus 2. And then we can say z equals sine of t, or z minus 0, but we don't need to write that part. So those are our x and z. Now we said x equals y, so y is also cosine of t plus 2. So that's our solution. We just saw a square plus a square equals a constant. We knew that had to be a circle, so we just named everything in the parentheses cosine and sine. Let's see the graph. Where'd my graph go? Here we go. So this would be 2 plus 2 cosine t. Y is also 2 plus 2 cosine of t. And z is 2 sine t. And now you can see the circle. I guess this is a circle. It's just tilted at such a weird angle that it looks stretched out. And if we animate it, we can see that the blue arrow is, in fact, tracing out the edges of it. I think my computer is getting a little overbooked, so I better finish this up before it gives out entirely. Okay. Last one is sketch this curve. And so that is a really complicated one. So in this case, you should just skip straight to the graph, because I have no idea how you would do this by hand. So 4 plus sine of 20t. I'm typing in another window so that I don't have to keep switching back and forth. 4 plus sine of 20t times cosine of t. 4 plus sine of 20t times sine of t and cosine of 20t. All right, let's see what that gives us. If we hit that, we get a funky spiral. Look at that thing. It is weird. Another slinky. But the reason why you'll notice, because it's look how fast that thing's moving. I can slow this down. I can say, let's just go from -1 to 1. Because everything in here is a trig function, that means everything's periodic. And so because of that, this whole thing, as weird as it is, will eventually come back on itself. In fact, it should go from -2 pi to 2 pi. Let's see if it can... If we do that, that should get one full cycle. Oh, no, that's too much. It would just be -pi to... Or 0 to 2 pi would be enough. What am I saying? 0 to 2 pi, that should go all the way around. Yep. All right, so that covers everything. We'll see you in class.